All right, video part 2 of Le Chatelier. Just continuing on. So, same thing as the worksheet. You're going to do all of it except for that number 4 calculation at the end. So, okay, here we go. I don't think this will not be as long as the other videos. So, oh boy, but I need to erase this stuff. Oh, and I was thinking that this cloth might be better than using instead of using the eraser. Okay, so example C. And let me see if I have my little, excuse me. All right, this one has AS4O6 solid plus carbon solid also. And it has AS4 gas plus 6 carbon monoxide gas. Now it says the following reaction takes place in the extraction of arsenic from ores. First, arsenic ore is reacted with oxygen to form AS4O6, which is then reduced by carbon. Reduced by carbon. That reaction is one you should be familiar with. It. A lot of times you can take a metal, or in this case a metalloid ore. Ore just means with oxide. And if you heat it up in the presence of carbon, that's like graphite, like this grounded carbon dust, the carbon will pull the oxygens off to make carbon monoxide, and you're left with pure arsenic. Okay, it's an interesting little thing. All right, so what would happen if you removed arsenic gas, AS4 gas? Okay, so back to our little thing, a little seesaw. So you take away the gas. All right, take away the arsenic. Now, to get back to equilibrium, you got to shift to the left, okay? Oh, no, Vela, bad. That was bad. If you take away the arsenic, no, it's going to go down the other way. Why not? I take it away? No. Taking it away makes this side lighter. I was not thinking. I was thinking to add it. So it's going to have to shift to the right to get back to equilibrium. So remember, if you take somebody off the seesaw, these guys are sitting on the seesaw, they jump off, boom. Hey, meanie, you just jumped off. So we got to shift to the right. In getting back to equilibrium, the system will shift to the right. The position will shift to the right. So now you'll have more of this, less of this. Well, let's see. They ask you. It's going to ask you. It will shift right. Number 1, and it says what will happen to the equilibrium partial pressure of arsenic. Okay. So, the partial pressure of arsenic 4. If you remove arsenic, all or some of it, okay, then what's going to happen is it's going to go out of balance. It's going to shift to the right to get back into equilibrium. This is going to be, it's going to be lower. It will end up being lower than initially. So just if it started out at 8, you take some of that away. Just say you take all of it away, okay? But when it restores back to equilibrium, this is going to go up, that's going to go down, and that's going to go down. But that is going to go, of course it has to go up to replace it, but it won't go up to where it was. It'll be a little bit lower than it initially was, all right? If you add more carbon solid, okay, guess what? If you add more solid, then it should have no effect, because remember, this is a system where it's like saturated. Yeah, okay. Even if you might say by adding more carbon, there's more possibility that can react with it. Well, remember the atmosphere above this is already saturated with all these 2 gases that it can take. So you have your solids down here. A solid there, and we'll say that maybe the yellow could be the arsenic. If I add more arsenic, you might think, well, that reaction should go faster. The problem is you've already saturated it completely. The part that's in equilibrium, well, these gases that are up here cannot change. You can't, let me see how that work. By adding this to it, this is not going to be changed. It's going to be no change. That's all. So, no effect. And then, what was the question? How will that affect the volume of carbon monoxide? No change. No change. V of CO, no change. Okay, now, how about, what if you add carbon monoxide gas, number 3? Actually, I'll say one more thing, too, just about that as well. You know that in, well, I don't know, I'll just put this little picture here. But you know that in your car, sometimes you put an air freshener, like a little solid piece, kind of a waxy material, whatever. Well, that air freshener is a solid, okay? And when you first put it in your car, you close it off. The car, you don't smell anything in the car. But then, as the time goes by, you know, it will vaporize and it will fill vapor up into the air. All right, here's the point. So say you got this vanilla air freshener. It is so vanilla in that air right now. It could not be more vanilla. And you could be sitting there with it while maybe you took a nap while this happened. You woke up. Oh, okay, so it's very vanilla inside here. Every very vanilla. And you know, some of it would have gone away. The solid would have gone down a little bit. Well, so the point is, if we add more solid of this, another air freshener in there, it won't get any. It cannot get any more vanilla-y. It can't be more vanilla. It's already as vanilla as it can be at that temperature. Now, if you increase the temperature, you'll see it more. In fact, you go to a car if you have an air freshener, and if it's a really hot day, sun, maybe you're out shopping, you come back inside the car, and it really smells strong because, yeah, it did go up a lot more of that evaporated out or vaporized out, sublimed. I guess it's sort of like in between sublimed and, yeah, vaporization as well. All right. Well, anyway, I just wanted to say that. So adding a solid is not going to change the equilibrium position, adding it. Even if I took away this solid, if I took away, as long as there's a little bit of solid, a little speck left, it will always have the same saturation level. So that's what I meant here, that those, adding more of that or taking away, if you don't remove all of it, it's not going to affect it. Adding carbon monoxide gas. Now, for this one, if I add more CO gas in here, now this part, see, yes, it is going to shift left. Okay? So you just have to pay attention about the solids. The solids, you need to pay attention when you have a solid with gases in equilibrium, or a solid like the salt water I showed you, solid, and you have the dissolved solid, the dissolved ions in the water. What I told you is true. Adding or taking away solid is not going to change any of the saturation. It's not going to affect anything unless you took all the solid away. You know, then some solid would precipitate. Okay, if you took some solid all the way completely out, then it would. But because it would have to replace some solid, it would not be at equilibrium anymore. Okay, now I forgot to finish that one. If you add CO gas, well, now what's going to happen is it's going to have to shift left. So it's going to shift to the left to get, as it gets, in order to get, as it reaches back to establish equilibrium, the position will have shifted to the left. And the mass of AS406, yes, it will increase. So now, even though adding or taking away solid, if you don't take it all away, will not affect anything. But adding more of this, it's going to shift left, and yeah, it is going to produce more of this and more of that. The mass of each solid will go up. And then number 4, it says, what if you add CO gas? Well, same thing. How will that affect the equilibrium partial pressure of AS4 gas? Oh, yeah. Okay, so you add more of this. We know it's going to shift left. How will that affect the pressure of AS4 gas? All right, let's think about this. So if this is increased, it's going to shift to the left. And when I say shift to the left, the positions, it's going to, material from this side is going to have to come onto this side. So these two are going to react more, and it's going to decrease that. So the pressure of AS4 will be lower than it was. Now I'm going to have to add a couple more on here. This is important. What if I added Oh, I don't really have to put this. You know what? I don't really have to put this on here because it's going to come up on the next one anyway. But well, I can just tell you, and then it'll be faster when I bring it up there. First of all, if we add a catalyst, that's actually the next little frame. I'll wait on that one, but I'll just say this: what if we added helium gas? How would that affect the pressure of, let's just say, AS4 gas? Okay. Let's look at two things. If we added helium gas into this tank, it's really small, but I'm going to draw it so you can see it. What's going to happen? Well, if you add helium gas, yeah, it makes more sense to put this on the later one that we see coming up. Well, it's actually not going to affect anything because helium doesn't react with anything there or there. Okay, so no effect. So added helium gas, no change. No change, no effect, no effect, no change. All right. The only thing it will do is it will increase the total pressure in the system. That's true. Whatever this pressure was and that pressure was of the gas, now that you have helium, the total system will have a higher pressure. Just like adding air to your tire. If you have these in your tire, it's inflated, and you pumped in some helium gas in there, it's going to make your total air pressure go up. But since helium doesn't react, it's not going to affect anything else there. Okay. Now, the catalyst. Remember we talked about catalyst in the last chapter. And all the catalyst does, you can look at the graph there. You might remember this must be what exothermic or endothermic. Since you in lower, it is exothermic. Adding a catalyst just lowers the activation energy, so it makes the reaction rate. It causes it to go. It causes it to go faster because it lowers the activation energy, but it does not affect equilibrium concentrations. That's an interesting thing to know. It does not affect equilibrium concentration. Just remember that. So adding a catalyst, you get to equilibrium faster, but you don't. But once you're at equilibrium, the numbers are the same as they would have been if you had not used it. Okay, so part two, after that, the effect of volume and pressure. Okay, this is a neat thing about equilibrium gas systems and Le Chatelier is pressure, and you think about it for a moment. Think about the pressure and think about the volume of a container. Like maybe if you had a container with a movable piston. What scientists do you think about? Pressure and volume. How do pressure and volume relate? So if I have a movable piston, so I've got gases inside here, I guess I'm going to have all these, N2, H2, and H3, N2, H2, and H3. Okay? If I increase or decrease the pressure, let's think about what can happen here. So, remember, Le Chatelier says that when you put a stress on a system, the system is going to shift in a way to offset the stress. Okay? Like, if you put too much weight on one side, this chemical on this side of the seesaw, well then it's going to react. It's going to shift that weight to the other side so that this heavy load that was carried by this side of the seesaw, now it gets spread out more between both of them and it shifts to the right. So, all right, here's another way to think about it. So, if we did something to increase the pressure of the gas in the system, imagine that if I do anything to increase the pressure, well then it would like to shift to the way to decrease the pressure, right? Well, that's a neat thing about equilibrium gas systems, that it can do that. And you'll see, okay, so for example, let's just say that I push this thing, whatever it is, I push it down way, 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 way low. Had a very, very small volume. If I compressed it way down, all these molecules are now a small volume. That means they're going to have a high pressure. So, can it do anything to offset the high pressure? Well, think about it. This reaction has 1 mole of nitrogen and 3 moles of hydrogen. So add that together. 1 plus 3 is 4 moles. Okay? You could say 4 moles, or you could say 4 atmospheres of pressure. You can just imagine in your mind, 4 atmospheres of pressure. This side only has 2 moles of gas. They're all gases, by the way. Got it? All right. Or 2 moles, or it could be 2 atmospheres of pressure. So if I totally compress this entire system, and it's at equilibrium right now, if I compress it, make it really, really small, it can shift to this side. If it shifts this way, there are less moles of gas, and now it can try to make the pressure come back to what it was before. So in other words, the system can lower its pressure. When you increase it, it can lower it by shifting to the right. So you always shift to the side that has the lower number of moles of gas. Always shift in the direction that gives you the lower number of moles of gas. It's written there in bold type in a longer statement. Okay, so here we go. So, we'll see it here. So number 1, example D. What will happen if I decrease the volume of the system? So decreasing the volume means I'm increasing the pressure. It can say both things. If you increase the pressure on this system, or you decrease the volume, then now, by decreasing the volume, you've increased the pressure, and so it's going to have to shift to the side with fewer number of moles of gas to the right. It will shift right. In shifting right, what will happen to the concentration of NH3? It's going to shift right, so that's going to increase. Number 2. What if I increase the volume, which decreases the pressure of the system? So I like to always remember, when I think about pressure in Le Chatelier, remember, if I increase the pressure, it goes to the lower number of moles. If I decrease the pressure, well, it doesn't like that either. A pressure drop, if you greatly increase this, it will have a lower pressure. Now it's going to go to the side with a higher number of moles. So you can always just think it'll do the opposite. If I increase pressure, it goes to smaller number of moles side. This side has 4 moles of gas, it has 2. If I increase the pressure. If I decrease, it'll be the opposite. It means it'll go left. So it shifts left. And now I've got to tell you one more thing about that in a minute. I want to add on. It will shift to the left. What will happen to the partial pressure of H2? When you get to your new equilibrium established position, it will shift left. And so, since it shifts left, material that was here moves this way. It reacts and it comes into the form of NH3. It leaves the form of N2 and H2. So that's going to decrease. The other thing I was going to mention, if for some reason there's a reaction where, let's just say this side had 2 moles, and just pretend it was 1 plus 1 is 2, that's 2. I mean, it's not balanced, but pretend it was. If you only had 2 moles here and 2 moles there, then increasing or decreasing the pressure of the system will not affect. It will have no effect, okay? So I guess I didn't put one like that on here. You might want to remember that too. And then last, add neon to the system. Okay, if you add neon gas, that's the same thing I told you before. And what will happen to the pressure of NH3? Can you remember adding neon? Since neon is a noble gas, it doesn't react with anything. So what happens to the pressure of NH3? Then it's going to no effect. So no effect, no change. Now, what could I do here? This one doesn't have a very good example of that, but oh well. I was trying to think of another one to add. I guess I'll just have to move on. Oh, actually, example E is the same thing, and I can continue this on with E. Yeah, that'll be good. I'll be able to add a little bit. I do want to tell you one other thing. What if we added a chemical that reacted with one of these? I can't really. Can I think of something? Well, yes, I could think about this. If you were to have NH3 gas, I'll just tell you this. This is just a bonus thing. If I were to add hydrogen chloride gas, now this is not hydrochloric acid, but it's HCl gas. If I added HCl gas, it reacts with NH3 to make a solid of ammonium chloride. Now, you should actually know that. You need to. That's not bad to a little memory one to memorize reaction. Ammonia and HCl, gas, gives you ammonium chloride solid. So if I were to add HCl gas to this system, this would be like an advanced question on the AP. They could ask it like to get like a 5. Well, the HCl gas is going to react with NH3. It's going to take away NH3. So that means it is going to cause it. This is going to be decreased. So if you add HCl gas, it's going to attack the NH3 and make a solid, okay? So it pulls that gas out of there. Now, let's just say you don't overpower it. Just say that I don't know, you put a smaller amount than that had in ratio. So HCl gas, just a little bit of HCl gas. It'll take away not enough to overpower it. So when it reacts, let's just say they completely react. That one completely reacts and it makes a solid. And so you still have this left over. So HCl gas reacts, takes away some NH3. That's gone. So it's going to shift to the right again to get back to equilibrium. It will shift back to the right. And that will be the direction it goes, right, to get there. Okay. So anyway, I just wanted to add that little bit in. All right, and then the same reaction is on question part E, question E. But now they talk about endo and exothermic. This is actually really easy, so I can just throw this in, and we're almost done. I know it's like an hour-long lesson when you put the two videos together. But I kind of already told you this as well. Always, when it comes to exothermic, endothermic, always think of a reaction as heat as being a reactant or a product. Okay, and I'll show you. If they say delta H is negative 92 for this reaction, I can go on and take that away. Delta H, well, I'll write it above here. Because I'm going to have room to fit where I want to put. Negative 92 kilojoules for this reaction. Thermo. Does that mean does heat go in or heat come out? The 92 kilojoules is on the right. So, if you've been following my seesaw example, then it's very easy to answer that question. So now, think of heat this way. If I add more heat, well now this side's heavy, it's going to shift to the left to get in equilibrium. If I take away heat, then it's going to have to shift to the right to get back to equilibrium. So, now when you change the temperature though, it also will change K, and you'll get a new K value resulting. And we will get back to that at a later point. So we'll talk about how to determine, well, what's the new K value going to be? It's going to be higher or lower than the original K value. And that's not here yet, but it'll come up after the next lesson, I believe. So, or I'll bring it up if not. So number one, if I increase the temperature of the system, will it shift left or right? So increasing the temperature, as we just said, means I'm adding more kilojoules to it. So boom, we're out of balance. It will shift left to get back to equilibrium. It will favor, you can also say instead of shifting, it will favor the reverse reaction, and the forward reaction will be less favored. So this will outnumber it until they get to the new positions. After new positions, you'll find that the concentration of NH3 will now be lower than it was to begin with. All right, number two, if you decrease the temp, well, then it's going to go the other way. It's going to shift right, decrease temp, take away the energy, the heat that was there, so it's going to have to shift to the right. And when it gets to its new position, the partial pressure of H2 will be lower than it was to start off. Because shifting right means more of that reacts, and it takes away the hydrogen, some of the hydrogen at least. Okay, and then if you add a catalyst, here it is finally. I don't know why I didn't mention it on the other one. If you add a catalyst, well, I don't know why I wrote that down, but what's going to happen to the equilibrium? It will nothing, no change. It just gets to equilibrium faster, but there's no change, no shift, okay? And so then what will happen to the N2? It just stays the same. So N2 stays constant, or stays the same. Constante. All right. So I have the little energy seesaw there at the bottom of it for you, and we did it all there. So there's probably something here or there that I can add in, but it'll come back. I try to think of every other example that I could think of. But yeah, I think we covered it all. All right, so you can do it all. About an hour long for that lesson, the video, and then to get that worksheet. I'll see you guys.